Hey, good afternoon. I'd like to welcome you to the DEHN Protects webinar series with today's session, Bond That Metal Stuff. And I'd like to introduce myself, Mark Hendricks, and my co-host, Stephen Weber.
Hello, everybody.
Yeah, we really appreciate everybody's interest in our exciting topics on lightning and lightning protection. Here's a quick snapshot of the webinar series with today's session on April 30th and a little teaser for next week's session on May 7th, where we'll be introducing some direct application methods of the topics that we've been sharing up till now, with a focus on today's session, Bond That Metal Stuff. The topics we'll be addressing in detail is earthing, which is important as an aspect of bonding, and we'll cover separation, side flash, how to eliminate, and we'll do a really nice deep dive into surge protection device application, which is a nice teaser for the photo on the side showing one of the first SPDs that was introduced to the market in 1954 for low voltage protection. So let's move along and get into the details of our topic today. Well, it really goes back to the pillars of protection that we've been discussing in our webinar series. Today's focus will be on the earth termination system, separation, and equipotential bonding. And we'll see that these, of course, these all interlink as part of the overall lightning protection system. Up to now, we've covered in detail the earth termination and the down conductor systems, but it all comes together as a complete set of elements that you have to follow for a complete lightning protection system, both the external, and today we'll be talking a lot about the internal protection methods. So I'd like to show our earth termination slide. We talk a lot about earthing as part of a lightning protection system. Earthing is also important, of course, for electrical power safety as well. But this slide gives us a really good look at the type A and the type B earthing electrode system. The type A consisting of horizontal radial earth electrodes that we see very common when you have very rocky soil where you have to bury the electrode, but this is in contrast to what you see very common, certainly at your residential main service entrance. You'll have a vertical earth electrode, a ground rod. And of course, there's a lot in the electric codes that tell and give you advice about how deep the rod should go, how what the actual earthing impedance that you're looking for. Residential, 25 ohms. A lot of industrial applications, they want up to 1 ohm maximum earth electrode impedance. And then we talk a lot about the type B ring earth electrode, where it's a grid around the system. We see a lot of this application that looks a lot like a ring earth electrode at power plants, where it's a large mesh, a large matrix of interconnected rings. And then there's a great discussion about foundation earth electrode, which is essentially what you hear a lot is the UFR ground, which is buried in the local concrete and within the structure, the actual cement and rebar structure. So this is a nice introduction to that, but it's really important because it all ties together with our topics today, where we'll be focusing a lot on bonding as well. So the minimum length of the earth electrode, this question has come up several times and I'd like to present it again. What we know about the IEC systems, they dictate class of lightning protection. The more severe class of lightning protection, class 1, requires a deeper and a more electrode contact with the soil. So if the soil resistivity is very high, as in dry, stony soils, you might have a very high soil resistivity. You need more electrode in contact for the more stringent class 1 lightning protection classifications. And this allows the control of risk. The higher the class 1 is the highest class of protection, that controls the risk of lightning damage. So the earth electrode has to be in lockstep with your class of protection. And a less severe class of protection, where you have perhaps less risk of fire and loss of life, then you have a more relaxed electrode system. And so that enables you to use a chart like this to understand your soil resistivity and then apply an earth electrode system suitable for that class of lightning protection and risk control. So that's what's really nice about a slide is this. It shows you the earth electrode helps control that lightning damage. So this is a really nice slide because it shows you the external lightning protection system married to the bonding in the earthing system. And so what's nice is we can show that the down conductor system is actually embedded in something that looks like that concrete pillar, and we're talking about equipotential bonding, we're talking about earthing, and it's all married together in a well connected and reinforced system. So here we have a nice illustration showing that earthing system, and it's the down conductor system married and bonded to the foundation earth electrode. And this allows you to have accessible points to install additional earthing and bonding around your equipment. So here we see these yellow pads would be bonding points within and married to the cement columns and the rebar systems. So in a system like this, you could use the buried down conductor that's immersed in this concrete as your down conductor system, and it's bonded with the structure. So the point of grounding and bonding always comes together hand in hand. And when you have equipment you might have an electrical control cabinet that might be sitting near this column and when the structure is complete, and you'll have access to that earthing electrode and bonding system with these yellow connection points. And these would be immersed in the concrete and give you a bonding point. That's what's important to remember. So we'll look at the earth termination system also bonded into the actual floor structure and the concrete around the building and embedded in the concrete floor. So this is all part of grounding, bonding of the structure with the earth termination system. And you can see that it would be a well-connected system with dedicated conductors and connections for the purpose of lightning protection that will prevent that arc and spark that you might get in a system that's only casually bonded. If you've seen a lot of rebar installations, you might notice that a lot of times the rebar is only tied together with wire hangers. And that is not necessarily a connection that's for the purpose. And so that's why it's really important to have exothermic welded joints and connected systems that are rated and designed for the actual connection to the reinforcement of the mesh. So when you're looking at a system, this bonding and equipotential system also provides shielding as well as equipotential bonding. So what's important here is you might have these mesh systems embedded around the structure. And this provides what looks like a Faraday cage, an electromagnetic shielding aspects. And that's what's important about the bonding. You need to bond and ground that system and earth that system to provide suitable electromagnetic shielding. This is really important in sites where you have high electromagnetic radiation, for instance, at a transmitter site or at a radar installation for air traffic control, for instance. What you would see in this environment is that the high intensity radiation fields will cause the electrical sparky, that arcy sparky that you see. For instance, if you've ever thrown a piece of tinfoil into a microwave oven, you'll see that microwave radiation will light up and cause sparks to be induced into the metal foils. Well, that's the effect that you would see if you do not have a connected bonding system. So that's why you'll see a lot of emphasis on shielding and electrical potential bonding networks. So now we talk about the equipotential system with the master bonding bar that you'll see right at your electrical service entrance in a facility. The mastercal electrical bar, the mastercal earth bar, it's essentially that first point of service entrance that the electrical service comes into the building, and the very first thing you do is you bond with your neutral ground bar. So this you see in some of our illustrations here is depicted as that master earth bar. And you'll see a lot of structures that look just like this, where we've got that master bar, and then all of the main grounding features of the building will come to this master ground bar. That way you have a single point of earthing that's exposed that you now connect all of your electrical systems to. So you'll see this very commonly at your home. This would look like the National Electric Code Article 250 earth bar going into the soil, and then you'll have a earth bar within your electrical service panel. At larger facilities, this would appear as a dedicated master ground bar. And that's what's important about an illustration like this, is that you see it's the single point of contact for all that earthing. So I mentioned it already, at your service entrance, you'll have what's called your neutral ground bar. And this is what you see in Article 250, what you see in the IEC standards, the British Standard 7430, they all agree. You have to have a single point of bonding for your neutral and your ground. And this establishes your electrical reference. It provides touch safety of all the metal. It provides a fault path. And this is how you eliminate noise and interference in your electrical systems. Now, what's important about an illustration like this is that you'll see that your neutral is now carried through the system, and the earthing is what's provided for your fault protection. And what's really important is that that neutral ground bond only occurs at one point. And that's what I mentioned about all the standards. They all agree you do not provide multiple neutral ground paths. That would create the opportunity for what's called ground loops, and it would certainly introduce a lot of noise potential. In doing site inspections, you can sometimes see where the electrician might have made a mistake and had a duplicate earth neutral ground connection, or perhaps mixed the ground and the white and the green wire, for instance, in the electrical system. So an illustration like this is really important to point out bonding. The neutral ground bond is for electrical safety, and it's a single point of neutral ground bond, and that's common throughout the standards. And this is a really nice photograph that I've used in the past. And bonding at the master ground bar, what could possibly go wrong? Well, perhaps a loose nut or excessive neutral earth currents could introduce excessive heating and excessive currents on your bus bar. So an illustration like this, a photograph like this, shows you really bad practices. You've got perhaps loose connections, you've got a mixture of connections. So what's important here is to really pay attention to your neutral ground bar and to really pay attention to the connections at your master ground bar. So now we move along to separation. If you can't bond it, you have to separate from it. So in your lightning protection system, we have the IEC standard dictates what's called the separation distance, S, the separation distance. And this is intended to provide separation to avoid side flash. If this building is struck by lightning and it enters into the down conductor system, You do not want the side flash into your adjacent electrical systems. So back to the concept of either bond it or separate from it. So here we've got a nice illustration showing a air termination rod separated from your victim with the sufficient spacing to avoid side flash. And what we see in NFPA is what's called bonding distance. It's essentially the same thing, and we've been able to show algebraically that the bonding distance D is actually the same effect of separation distance. And that's what the NFPA standard dictates, is that if your down conductor system runs adjacent or next to or near to metal bodies, you have to connect to it or provide sufficient spacing away from it. And this is essentially identical to the LPL3 of an IEC system. And as I pointed out earlier, LPL3 is a less severe control of risk. So the IEC system allows you to have even more control of separation, which would be even more spacing for the more severe lightning strikes to control more risk. But essentially, the NFPA and the IEC systems provide a very similar definition of what's considered that separation distance. So this illustration is nice because it shows you all of the factors all in play simultaneously. And we can look at the actual air termination system. You can follow the down conductors. You can see where the metal is bonded, and you can see where we can apply separation from victim equipment that you do not want to introduce lightning currents. You do not want to introduce side flash. You've got things like your solar panels that you separate from the air termination system. You've got things like a radio antenna that you separate. You've got security cameras, light pole cameras, Wi-Fi transmitters and radios that you want to separate from your lightning protection system. So this is one of the points we make, that when you install a lightning protection system for external lightning protection, you have to pay attention to all the aspects: the down conductors, the air terminals, but also the bonding and the separation from the lightning protection system. We've shown in our other sessions very similar types of systems where you have an isolated air terminal that connects to the metal body but has a separate earthing system with a separate earthing reference. And we can use some of our lightning protection products that provide side flash separation distance with the ability to conduct the lightning currents into the earth separate from the grounding system of something that might look like a air traffic control radar system. And again, remember, we talked about that high intensity electric fields from radars and such, that HERF, where you don't want to have unbonded metal. Unbonded metal would produce arc and spark, and it would produce things like incendive sources and noise into the electrical system. So unbonded metal is really a really big problem on sites. We also talked a little bit before about isolated air terminal systems for very expensive assets like a rocket filled with rocket fuel and hydrogen and oxygen, where the introduction of lightning side flash would essentially destroy the asset. And so we see isolated air terminal systems that effectively provide lightning protection with separation from the victim. So you're either separating from it or you're bonding to it. And remember, lightning protection systems include all 5 aspects of that pillar of protection. And if you ignore any of them, you run the risk of flashover into your electrical systems. And that brings us to bonding and SPDs. So what is an SPD? What does it do? Well, what an SPD does is it provides electrical bonding through the SPD for voltage control. So direct metal to metal provides equipotential bonding, equal voltage. Well, that is essentially controlling the voltage so that you don't have sparks between your metal elements. And an illustration like this is really nice because it shows you you've got your earthing system bonded to the master ground bar, the master electrical bar, the master earthing bar. Well, that's bonded to the earthing ring, separate and buried, separate from the lightning protection down conductor. Remember, you don't want to bond into your electrical down conductor with sensitive electrical equipment. You want to have a dedicated bonding connection into the earth ring. Now you look at things like your black gas pipe. Well, that pipe is bonded to that earth bar. Or you might have things like copper pipes in your structure. Those copper metal pipes are also bonded to the master bar. But now look what you've got. You've got surge protection devices that are bonding to your electrical equipment. So your main electrical power, your telecommunications, your low voltage data systems, and your other important data control systems are connected through the SPD to provide voltage control. That's what an SPD does. It essentially bonds during the lightning event, during the surge event, and provides control of voltage and gives the surge current a path into the main earthing bar and then into the soil. And remember, you want to apply surge protection devices on all of these incoming lines and don't leave a back door for surge damage. We've seen lots of applications at places like PV farms where the customer has done excellent work with all of their other aspects, and they've left out, for instance, SPD devices on the low voltage control signals. Well, when that low voltage signal comes back into your critical systems, it will allow a backdoor for surge damage. So that's why we use that term backdoor. Don't allow unprotected wires to come into your critical infrastructure. So how SPDs work? What are the features and benefits of an SPD? Well, SPDs basically can be described as series connected or parallel connected, voltage switching or voltage limiting type technologies. There's also a further distinction between series and parallel with filter elements like inductors and capacitors and current limiting components like fuses and breakers. This allows, when combined, a very wide range of permutations so that you can develop surge protection devices specifically for that electrical equipment protection. And you would see this because an SPD for a main service entrance is different than what you would use as an SPD for a power over Ethernet circuit. And this schematic here to the right shows us a nice illustration. You have a combination of what are described as spark gap devices with a series fusing element with a high performance silicon avalanche diode on the protected side. So in this case, you might apply a series protection for a high-speed data network. In this case, what might be described as a 4-wire, for instance, RS-422 circuit coming from a security gate controller outside of your structure. And this allows for the protected side to be closest to your I/O control panel and your fire and safety alarm circuits. And here you see that combination of series and parallel devices with series and parallel elements to give you the fine-tuned connection that you're looking for. So how do SPDs work? We have devices that you recognize as gas discharge tubes or spark gaps, and or what we like to consider voltage switching devices. And what that means is, as the voltage rises, it reaches a peak and then switches on. And this is usually seen as a dielectric breakdown. For instance, in what might be considered a spark gap device, the gas inside of this small element will ionize and then spark. And you'll see this actually when you test these types of devices, you see them actually glow as the currents and the voltage produces enough breakdown to cause a small dielectric breakdown within the device. DEHN manufactures very effective AC devices that work on this same principle, where the voltage reaches a high enough level and then it switches, voltage switching. This is in contrast to what are considered voltage limiting. And in this curve, you see that as the voltage rises, very little current flows, and then at some what's considered the turn-on voltage, you hear it often called the turn-on voltage. In a Zener diode, it's called the Zener voltage. Well, essentially what's happening is you get to a voltage limit, and then the device turns on and controls the voltage. In many applications, you hear the term clipping. In the audio industry, you hear distortion. Well, that's when the devices are clipping and causing nonlinear distortions in the signal. In AC power protection, these devices are very effective because you can apply them and the AC sine wave sits below that turn-on voltage and essentially is dormant until the point where there is a spark or a voltage spike that then causes the device to turn on and limit the voltage. So there's a wide family of sizes, shapes, colors of types of devices like this. And what's important is that these are just a snapshot of the types of devices that you can use to control that voltage. And of course, these applied in series and parallel then can give you any number of permutations for high power protection and low power control circuit protection. A slide like this we could talk about in great detail, and I'm sure there's lots of questions about what are the advantages between types of devices. Do they have a fast turn on? Do they allow more leakage current, which might cause noise in your electrical circuits? And when designed appropriately, these devices can be put to great advantage in your electrical protection systems. And again, this is just a snapshot of the types that are available, but this is essentially the tools that designers can use to put into a protection system. So, features and benefits. Well, what's the benefit of having a large service entrance protection? Well, now you can control that voltage that might be coming in on the AC power or on the neutral ground bar. If the ground potential rises high enough, it still induces voltage and currents into your service entrance. And here you see what can result. Even with the application of surge devices, they can be undersized. Remember, we talked about applying these devices effectively. If you have a very high power AC service entrance with a very underrated device, you can have damage input right at your service entrance. What's important about the service entrance is to be sure to apply lightning protection SPDs that are rated for full lightning currents. And these are just examples showing the introduction of fire from the surge event. This was not actual lightning direct strike. This is lightning that's coming in and the surge protection device is trying to control that. Here's a couple of nice photographs of what can happen well within the building. This is not at the service entrance. These are at the AC power outlets or at the phone jacks within a building. And here you can see the fire damage that you can get from what are actually small wires. We're not talking about main lightning currents. We're talking about smaller currents that still created enough damage to introduce fire hazard into the building. So in both NFPA and IEC, we described the lightning protection system, the external protection with your air terminal, down conductor, and earthing electrode. But all of the standards still dictate that you need to apply surge protection devices to further control the risk of fire. And this is what could result with inadequate surge protection devices. So we talk about feature benefits. Well, you want to have the features in your SPD to provide suitable benefits to provide reduction of fire risk. And here's some very, what you would consider a lower fire risk, but it's still proved to cause damage into what might be a telephone service entrance control panel. And here you can see that even on these small gauge wires coming into the telephone circuit, it's still enough voltage to produce fire damage and electrical damage on these circuit boards. And here you can see the controllers on something as important as your electrical washing machines. The electrical damage on such circuit boards can cause substantial loss of equipment value. So you want to control voltage spikes where you cannot equipotential bond your electrical wires. And that's what we see in this illustration is you're applying surge protection devices throughout the building at critical junctures to adequately control the voltage on your AC power and on your data line. And here we see some illustrations of data circuit protection. Perhaps you've got power over Ethernet cameras throughout your building, and you want to protect that exposed camera and that back door for the voltage to come in and otherwise pollute and cause damage into your system. So AC power protection comes in many flavors. DEHN is happy to provide a configurator on our website where you can easily find your electrical voltage and then get to the SPD type of a device suitable for your electrical power configuration. And what's important on this slide is showing that you want to place your SPD, your very first important SPD, right in front of your main system to provide the most effective control of your electrical power. But remember, in a system, there may be branch circuits that are also delicate, and you want to have SPD devices perhaps downstream from your main. So in this illustration, you can see that if there's a ground potential rise, your SPD will control that voltage between the earthing and your electrical service. But remember, downstream, you still want to apply coordinated surge protection devices. So here's an illustration of our alarm panel type protection, where you've got many types of delicate electrical circuits that for an alarm panel are going to be very important for security of your facility. And you've got things like exposed contacts that are either outdoors or near the external of the building. And what's important is that you're providing surge protection devices to prevent the alarm panel from being destroyed, which would, of course, defeat the entire security system. So in an illustration like this, you can see that you've got a full array of backdoor type circuits that can bring electrical damage into that alarm panel. This is a couple of photographs that I've seen at electrical sites, and this is quite literally my pet peeve. Floating metal that is not bonded. So in this photograph to the left, you see some metal structures that are supporting things like flow transmitters. And if you're able to see in enough detail, there's actually no electrical earthing on these metal struts. So if there is electrical surges in this circuit, this metal is unbonded. and will in fact produce even more ground potential rise. A lot of times I've heard designers say, well, I don't want to bond this metal because if there's a lightning strike, it'll be affected. If there's a lightning strike, it'll be even more affected because it's not bonded, which now introduces a huge voltage ground potential rise into this circuit. And in this case, we're able to trace the wires back into a data control system inside of a cabinet, and there's no surge protection devices installed here either. So in this case, the actual solution to a problem like this is to put bonding on this metal, surge protection devices at the flow meters, and surge protection devices inside of this control cabinet. So remember, you're looking for all those back doors into your electrical control systems. So there's a wide variety of surge protection devices available for both the AC protection and the data protection inside of such an electrical control panel. And this is directly drawn from the NFPA 780, and this is for solar power PV protection. And what you see is the application of SPDs at several locations within the structure. This is an introduction to that concept of coordinated systems where you've got SPDs out at the actual solar panel frame and SPDs located at the combiner circuits, the inverter circuits, and then again, surge protection devices on the AC side. The only thing that's missing from this particular sketch is the surge protection devices on the data networks that are also probably coming into the building structure. And this is an introduction to that term you see very often is coordinated surge protection, where you've got a main distribution circuit and you'll apply surge protections on the mains, but you'll also have downstream panels. And I talked about that in a previous slide where you've got branch circuits that also need to have surge protection devices. And this is an opportunity to have that coordinated system. And I like to use the term point of use. The closer you get to your very delicate electrical apparatus, the more important it is to have a surge protection device at that point of use, not just at the main service entrance. You want to coordinate that SPD with the point of use. You also want to watch for things like electrical backup generators and transfer switches. And you also have to pay attention to step up and step down transformers, where the transformer introduces a new neutral ground bond. So you need to really pay attention to your bonding and your coordinated surge protection devices. And coordination is critical to what's considered the zone concept within IEC 62305-4. And this is what's really nice about a slide like this. This shows you almost all of your aspects. You've got your direct lightning currents that would attach to your air terminals. You have your down conductor systems. You have your earthing systems. But you also want to provide surge protection and additional bonding through the system. So here you might have your main electrical service entrance, and that might feed a branch circuit on the floor of a hospital, which ultimately goes into a very delicate operating room. So this is a great example of the more protected zone having more control of risk. And IEC does a great job of providing guidance into how to select the devices, where to place them, and then how to bond them in with your electrical service. So here you see the main service entrance AC protection with that delicate point of use protection for both AC power and your data networks that you'll see, your IT equipment. And of course, in a hospital, there'll be elaborate IT equipment. And if you're the patient in this operating room, you'll want to make sure that the designers had installed suitable earthing, bonding throughout the structure, and that's what you see here, the electrical bonding, but also the voltage control, the essentially your power protection and your data protection with suitably sized and rated surge protection devices for a coordinated system. And that is what we covered today. We talked about earthing, we talked about bonding, separation, and if you can't separate it, you got to bond it. And if you can't directly metal to metal bond it, you apply surge protection devices. And that helps give a full look at the pillars of protection. And I think that gives us some time for questions. Stephen, I'd like to open it up if we have any questions that have come in from the audience today.
Yes, Mark, we have a question, and I think this already addresses one of the most important questions we normally get. He's asking, what is the difference between an IEC Type 1 and a Type 2 SPD?
Well, allow me, I don't like to do this, but I'll back up one slide. So the IEC Type 1 device is considered to be rated for the lightning current that you would get induced from a ground potential rise. So a lot of times people are concerned that the lightning current is coming in on the AC power, which of course can happen. But on the AC power, you've got things like transformers and your meter base that can also provide some degree of actual isolation. But when the lightning currents come in through the down conductor and get injected into the earth system, you have ground potential rise. And that in the IEC methods are considered to be a Type 1 device. And they're tested to direct lightning current withstand for a 10 by 350 pulse. A Type 2 device, which is actually similar to what's considered a UL type device, is ideal for downstream protection, where you're past the main service entrance. And I think those are some of the most important aspect you see between Type 1 and Type 2 is the rating with a 10 by 350 microsecond pulse in the IEC methods. I think that provides some background to that.
Yes, yes. I'd just also like to mention that as you move closer to the terminal equipment with a coordinated system from a Type 1, a Type 2, and a Type 3, like Mark illustrates in the slide, you also have smaller voltage protection levels, meaning that the amount of voltage that the equipment is now basically exposed to, it just keeps on getting smaller and smaller and smaller. So you have this progressive protection scheme addressing even more sensitive equipment. Then Mark, we have a question. You mentioned the 3 different technologies that SPDs are designed according to. Can we use these different technologies and combinations to address advantages and disadvantages of each other to form a total SPD design that is acceptable?
Yeah, that's a really great question, because it is possible to coordinate the different types of technology, but I like to use the term, they don't play well together. What you generally find is things like silicon avalanche has a really great response and a really low voltage threshold. And if you just simply take a silicon avalanche diode and mount it next to a voltage switching element without considering the coordination between them, oftentimes you see something that might be a decoupling mechanism that forces the 2 devices to coordinate together. And in an illustration like this is actually a really nice illustration where you can see there's some distance between the Type 1 and the Type 2. So for instance, if I put a voltage switching element right here at Type 1 and a metal oxide element at Type 2, the distance, that inductance of the wire itself, will serve to decouple the 2 devices. So the instant that the Type 1 turns on gives the Type 2 a little bit of time delay so that it doesn't turn on too soon. So it is possible to coordinate them, and I've seen some really excellent products that provide excellent coordination with that built-in mechanisms, but usually there's something like a decoupling element. We had a schematic earlier where we showed that difference between a spark gap and a silicon avalanche, and there was a series element to force the 2 to respond together. And that's really what you need to pay attention to.
Yeah, so I just want to add, so you can have a combined type 1 or type 2 and type 2 device into the same package.
Yes, it is absolutely possible. Yep.
Then what are the disadvantages of using an SPD with a higher nominal voltage in a smaller voltage circuit? In other words, if you have a SPD with a 20 volt DC nominal voltage rating in a circuit that is a 12 volt DC circuit, what is the disadvantage of using that?
Well, the idea would be to put it as close as possible to your operating voltage, but what you often see is that it's just not practical. The disadvantage is that a little bit more voltage will rise before the device turns on. So you have what might be a voltage limiting device that limits a little higher than what would be ideal, but you get into the practical considerations. Maybe the circuit is floating, and if you might have a 12 volt circuit, but it could actually float between 12 and 24. And if you tried to protect too low, you're actually causing a nuisance. So there's several limiting factors that might prevent you from using what you think is the most ideal component. And it really does come down to how sensitive that circuit really is. So you want to apply the most stringent limiting voltage control, but it may not be practical.
Yes, I just want to mention as well, while we're on the topic of voltage control and voltage protection levels and those type of ratings for surge protection devices, remember that a surge protection device will have this voltage protection level rating of a certain amount of voltage. But remember that when you install this surge protection device into a panel and you have conductors from the power bus bars to the SPD and from the SPD to a grounding connection, the voltage drops that you are going to see over these conductors need to also be taken into consideration, as these can increase the overall voltage protection level that the device will provide. So it's very important to take that into consideration when you install SPDs as well. Mark, can a SPD be grounded through the incoming feed cable shielding, or is a dedicated ground conductor needed?
Well, my personal preference is that the SPD has its own home run connection back to the master ground bar. What you see a lot is something like a point of use device, like a power strip that you have your computers and your high expensive home electronics plugged into. That particular type of a device is protecting relative to the ground wire in the power strip. That is effective, but it's not ideal because you're dumping those surge currents back into your ground and your neutral wires. Although it's very complicated, it would be better to have a dedicated home run back to the master ground bar. It's just not practical in many applications. And just as a point of reference too for this presentation today, the application of SPDs in of itself could be an hour-long topic, which I think we'll plan for our upcoming webinar series, because this really is a complicated and important subject of its own. How to select, what are the, Stephen, you also mentioned, what are the surge current ratings? It's not just important to have a huge surge current rating, it's important that the device actually can handle and withstand and effectively dissipate that current. So, for instance, I could put a giant surge protection device at my service entrance and have a little tiny ground wire or a little tiny fuse, and now I've just derated the whole thing, and it's almost a waste. So in our upcoming sessions in the following weeks, we're going to be talking a lot more about the actual application of solutions on a, for instance, next week we're planning wastewater, and what do you actually need to do? So that there's a lot more insight to be gained from actually looking at some of those circuits.
Yes. I'd like to go back to the section before we did the surge protection devices. When we install, the questions is the English is not very good, so I'm just trying. The question is basically, how can we use the rebar if we're not sure that the rebar is electrically continuous from top to bottom. So is there something that we can do to make sure that the rebar is electrically continuous before we use it as part of the lighting protection down conductor system?
That's actually a really great question. There are a series of tests within IEC and within NFPA where you apply a 10 amp current into that circuit, and then you measure the voltage displaced by that 10 amp, like an injected current that then proves that there's connections within a structure. That's a test that I've seen useful for the earthing electrode. It's very difficult to go back and analyze a structure without something like a test like that, where you're injecting a high current and then actually able to measure the voltage drop to prove that it's electrically connected. Stephen, you may have some additional insight if you've seen that.
No, I agree 100%. I agree 100% with you. I mean, the test procedure that we have in the IEC standard allows us to calculate or to measure what is the continuity through the reinforcing. And we do that by means of that 10 amp injection current test. And the standard says that we have to calculate, or we have to measure there is a continuity that's 0.2 ohms or less. And only then can we use the reinforcing as part of our down conductor system. Otherwise, we have to install external down conductors. With some of the applications that we do these type of things, we run conductors inside of the reinforcing as well to ensure this continuity when we are early enough on the project. But obviously, if you're on the project being costed, it's a bit difficult.
Yeah, legacy building protection is a really difficult process. It takes a lot of, you really have to be there on the site and be able to conduct tests, as Stephen mentioned, with the 10 amp injection, and then be able to measure a suitably low voltage drop to prove that it's a 0.2 ohm circuit. So yeah, legacy building protection is a real difficult topic of itself, which is why isolated lightning protection systems are very attractive for designers to use in a legacy building, because now you're not counting on any of the structure as part of your down conductor, and you really don't need to worry about the side flash because you've provided isolation. Because you never know what's buried in the wall in a building that was a legacy structure.
Yes, and we have a follow-up question. When we are using all that rebar in the system, don't we need to be very careful about the separation distance? It seems almost impossible to maintain that separation distance with the electrical wiring, pipes, and all the other metal work. Any comments on that?
That's the perfect application for surge protection devices, because you're not separating and you're not bonding, but then you can control the voltage so it doesn't flash through the insulation.
Okay. What is the advantages of using a residual current circuit breaker or an earth leakage circuit breaker with an SPD?
Well, it really depends on the leakage currents in the system, and it allows you to control the and monitor the fault currents that might be also injected. There's, as I mentioned, this particular topic can go on for quite a number of slides, just looking at all the variations and permutations. This might be a really good one to follow up with and have a follow-up discussion.
Yes, I just want to mention that, remember, when we install surge protection devices into a power system, we have something that we call follow current and follow current limitation. And whenever we do have a lightning impulse or surge current, we want the SPD to safely divert this to earth and then go back into a high impedance state, so we don't have a very large power system frequency follow current that goes through the SPD. So in other words, we want the SPDs to really limit that power frequency current, that follow current that comes through the SPD, up to a point where it really isn't really sensed as an earth leakage or an earth fault in that sense. So you don't want to lose the reliability of the circuit every time a surge comes through. You know what I mean?
Right.
Then we have a question. Just trying to find myself. We have a question where Damien asks about bonding and separation, and Damien, I think you're asking is asking if there is any advantages of bonding and separation, for example, with a PV panel. Mark, I can just quickly mention to him that we had a discussion about separation distance and bonding, a bonded system and an isolated system in our previous webinars, and you'll see what we mentioned there is it's all about where you want to inject lightning current into. So in a case of a PV installation, you don't want lightning current really to be injected into your inverters and into your frames and even into the you know, sensitive communication systems that you have in large PV fields. So an isolated system kind of provides you that benefit or that advantage of keeping the lightning current separate from the system. While a bonded system, you basically inject everything into the structure of the PV panels and into the inverters and all those critical pieces of equipment. So that's the main benefit of keeping a separated system or an isolated system over a bonded system. Coming back to the question that we initially had about earthing, you know, through this cable shielding, we have multiple follow-up questions where people are asking if we do run a earthing, like you said, Mark, you prefer separate from the shielding of the cable. Is it okay to run that adjacent to the power cable? And does it need to be a certain a certain diameter, a certain cross section, like 75 millimeters, or is there any specification on that?
That would be I'd have to really look at that one in detail, because I'm trying to picture in my mind what this should look like. So this might be a really good one for follow-up.
Okay. Yeah, I think that's about it. The rest of our questions, I think we can address in emails.
And we will be following up with all the questions.
I see a lot of the remaining questions is specific applications of surge protection devices. We will address them. I don't think we'll take it offline and we'll address it to each of you guys individually, because there's nothing really in common in terms of these requests that people are asking about. Thank you, Mark. Very informative. Thank you, everybody, for joining us.
Thank you, Stephen. And I'd really like to send my appreciation to all the attendees for your attention and your time. Very interesting topic and great questions that'll help us in our follow-up webinars that are coming in the following weeks. Okay, thank you, and be safe out there.